Hello, everybody. Welcome to your Topic 6 ticket to retake. I hope that this helps you review, reteach, whatever you need if you would like to retake your Topic 6 test. All right, so our first couple problems, we're asked what are the key features of each graph, include domain, range, intercepts, and asymptotes. All right, so this is an exponential function. We can see that our variable is an exponent, so that's why it's exponential. The domain of these exponential functions is all real numbers. That goes from negative infinity to positive infinity. So all of the x's, you can plug in any x value and you won't run into anything that's undefined mathematically. The range, well, that could change. It kind of depends on what this graph looks like. Because this is a 0.3 that is less than 1, I know that this is a decay. It's going down like that. You could graph it on your calculator just to see what it looks like. This right here, though, we just want to make sure we're noticing that when it says x minus 2, that's a horizontal shift of your x values, and everything is going to the right 2 units. But it did not shift anything vertically. So your range, if there's no vertical shifting, all the y values will be greater than 0. So our range goes from 0 to positive infinity. And we do not include the 0 because, I'll skip to this one, we have an asymptote at y equals 0. Our asymptote is always y equals 0 until we have a vertical shift and then it changes. Let's see, intercepts. So because we have an asymptote of y equals 0 that's sitting right on the x-axis, so there are no x-intercepts, but we will have a y-intercept. Y-intercept we could find by plugging in a 0 for the x, doing the math. You could check out a table of values on a calculator. A couple ways to find it, but our y-intercept is at the ordered pair 0. I'm just going to say 11.1. I'm just going to use the decimal for my calculator. So those are the key features of that function. All right, number 2, same thing. We're going to run through the same questions, but if we take a look at this one, so this is our base, that's our exponent, exponential function. Because this 3 is greater than 1, this is a growth. So it's going to be getting bigger as you go along the x-axis. So it exponentially grows. This plus 4 on the end is a vertical shift. Maybe I'll just make a note that that means everything is going to go up 4 units. That will change your range and your asymptote. It also changes your y-intercept. You know, any shifting will change your y-intercept, but um, let's just answer these questions. All right, so domain, it's still going to be all real numbers from negative infinity to infinity. Now the range, if you have no vertical shifting, all your y values are greater than 0, but now everything went up 4 units, so now all the y values will be greater than 4. So our range will go from 4 to infinity, but we don't include the 4 so that we have all the values greater than 4. That brings me to the asymptote. The asymptote is default at y equals 0, but if we're going to shift up 4 units, then your asymptote shifts up 4 units as well, y equals 4. And then because we shifted up, we moved above the x-axis. There are no x-intercepts, but our graph will hit the y-axis somewhere. So we can take a look at a graph, table of values. Our y-intercept is going to be at the ordered pair 0, 5. Without that plus 4 right here, our y-intercept was at a 1, and then when we went up 4 units vertically, 1 plus 4 got us to that 5. There's another way to think about that. All right, so it says write an exponential function to model each situation, find each amount after the specified time. So a population of 1,236,000 grows. I'm going to circle grows. That means It's getting bigger and it's growing by a percent. So that's what an exponential growth is when you're growing by a percent every year. So it's growing 1.3% per year for 10 years. So exponential growth is our function f of x equals a times 1 plus r to the x power. So that a value is your initial amount, and our initial amount is that 1,236,000. 1 plus, by the way, anytime it's a growth, we do the 1 plus r. If this was a decay, we would do 1 minus r right there. Otherwise, your exponential models are the same except for a plus or a minus. So our r is the interest rate, but as a decimal. So 1.3% is a 0 point. We've got to move the decimal 2 spots to the left, or you could take that 1.3 and divide by 100, and we'll get 0.013. And then, so I guess when it says write an exponential function to model the situation, I'm going to leave an X there. So that answers the first question. There's our exponential model, or excuse me, our exponential function to model the situation. And then we could simplify this 1 plus 0.013. Maybe I'll do that in the follow-up question. And then we're going to find out the amount of the population after 10 years. So that's what we're going to plug in for that X right there. So we have 1,236,000 times. I'll go ahead and add these together, 1.013 to the 10th power, and then we grab our calculator and we type that in to see what we get. All right, so when we type that in, we get 1,406,413. I'm going to round to the nearest integer because it's a population, I guess I would assume, of people. So a decimal, a partial person wouldn't make sense. So that's what our population would be in 10 years. All right, number 4, a population of 752,000 decreases 1.4% per year for 18 years. So when we see decreases, that changes our exponential function we're going to use, and we're decreasing by a percent, so this is an exponential decay. So first our function, f of x equals, we're going to have our a times, instead of 1 plus, it's going to be 1 minus r because of the decrease to the x power. So if we go ahead and fill in our information, we've got our initial amount, 752,000, times 1 minus 1.4% is a 0.014 as a decimal to the x power. So there's our function. And then to actually answer the follow-up question is, well, what will the population be in 18 years? So 752,000 times, maybe I'll go ahead and combine that 1 minus 0.014. We get a 0.986, and we're going to plug in an 18 for that x. And then we grab our calculator and calculate this out. All right, so our population after 18 years, it goes down to 538,448. I am rounding to the nearest integer, just assuming we're talking about people or something where you can't have a partial amount. One thing just to notice, it could be a quick, check. This population started out at 1,236,000 and it was growing. Did we get an answer bigger than that? And we did, so that kind of checks out. If we got an answer smaller than this, then we made a mistake somewhere in our process of this problem. Number 4, here's our starting population and it decreased. So in the end, we should have a population less than that, which we do. So that all kind of works out and makes sense. All right, number 5. Darren invests $4,500 into an account that earns 5% annual interest. How much will the account be, how much will be in the account after 10 years if the interest rate is compounded quarterly? All right, so we got to circle the word compounded and quarterly. So we have a compound interest formula to use for a problem like this. That formula is A equals P is the principal, that's a finance term, that's our initial deposit or investment, times 1 plus R is the interest rate as a decimal, over N is our number of compounds per year. Compounding just means calculating interest. How often are you going to calculate interest in a year? This gets raised to the N, so there's that N again, number of compounds, times T, number of years. So when we see in a problem compounded something like quarterly, monthly, annually, something like that, this is our formula we're going to use. All right, so our P is the amount that Darren is investing, so 4,500 times 1 plus R is the interest rate as a decimal. So 5% is going to be a 0.05. N is our number of compounds. If we are compounding quarterly, that will happen 4 times in a year. So N is a 4. Raised to the 4 times, and our T is time, which is 10 years. All right, so we're going to get that all set up and then we will calculate it. All right, so after 10 years, the amount of money that will be in the account is $7,396. And our rounding on this one, we are talking dollars, so dollars and cents. We need two numbers after the decimal. It's a 0.287, which will round up to a 0.29, so 29 cents. So Darren puts in money. He lets it sit there for 10 years, and we're going to calculate interest 4 times a year at an interest rate of 5%. Our answer should be bigger. We're earning interest every year. And so when we get an answer bigger than what we started with, that's making sense. That number should not go down. All right, number 6, Ella invests $2,000 in an account that pays a 4% annual interest rate compounded continuously. All right, well, compounded, there's that word again, but this time continuously gets its own formula. What is the value of her account after 5 years? Round your answer to the nearest dollar. Well, that's a specific. We'll make sure we round our answer to the nearest dollar. Show your work. Well, of course, we are going to show our work. So anytime we see compounded continuously, we have a compound continuously formula. That is A equals principal times E. Remember, E is the new number we learned about in this unit. It's kind of like pi. It's used so often in higher levels of math that it gets its own symbol. It gets its own spot on a calculator. You guys are seeing it for the first time in Algebra 2, but that's that E it's a number. It's nothing. It's not. You don't plug anything in for E. It's just a number. Raised to the R times T. R is the interest rate as a decimal, and T is your time in years. All right, so our P, Ella is investing $2,000 times E raised to the power of, the R is 4%, so 0.04 times the time, which is 5 years. So what this means, compounding continuously, we're just constantly calculating interest. Continuously, continuously, continuously. How much money will she have? So it's not happening just 4 times a year, like in the previous example. How much money will she have when you are compounding continuously? All right, so that's going to give us 2,442.8. That 0.8 is going to run that 42 up to a 43. It did say to round to the nearest dollar. So $2,443. So she put money in, she let it sit there for 5 years, and when it's compounding continuously, that's how much money will be in the account after 5 years.